Hi, let us continue with our discussion about the design of reinforced concrete peg footing subjected to axial loads together with the moment acting in the major axis. Previously, we talked about the design of reinforcement resisting the moment due to the soil pressure at the ultimate limit state. We design the reinforcement both in the major axis and the minor axis. We need to provide sufficient amount of reinforcement bar so that the AS provided is greater than the AS required. And then we need to check the AS provided, making sure that it falls within the range of the maximum and the minimum bar areas. Once this is completed, our next step now it will be checking the shear resistance of the peg footing. We're going to discuss about this in this video. In fact, there are three types of shear load that can cause a peg footing to fail. We first deal with the shear loads at the shear plane located at 1D from the column face. We're going to check for both the major and the minor axis, making sure the peg footing have the adequate resistance to the shear force acting at the plane. The shear plane in the major axis located here, which is 1D from the column surface. As for the minor axis, we are referring to this plane, which is also 1D from the column face in the minor axis. First, we need to determine the locations of those shear planes. Get the effective depth first. We have two effective depths, one in the major axis, another one in the minor axis. This was calculated previously while designing for the moment resistance. The formulas is given here. The effective depth is determined from the top surface of the peg footing to the centroid of the reinforcement. To determine the effective depth, you need to use the thickness of the peg footing minus the concrete cover minus half size of the main reinforcement. You get the effective depth in the major axis. As for the effective depth in the minor axis, you use the thickness of the peg footing minus the concrete cover minus the bar size of the main reinforcement and minus half of the bar size of the secondary reinforcement. That gives you another effective depth which is slightly smaller than the major effective depth. Then we will need to determine the XZ here so that we can quantify the total shear force acting at this region. As for the minor axis, we need to get the XY. How do you get the XZ and XY? You can sketch the plan view of the peg footing. The width of the peg footing in the major axis is equals to 2.4 meter minus the width of the column, which is 300 mm, divided by 2, that gives you Z1, minus the effective depth, you get XZ, which is 556 mm. You will do the same for the minor axis. Take the width of the peg footing, which is 2.2 meter, minus the width of the column, which is 150 mm, divided by 2, you get your Y1. minus the effective depth. Now you get your xy, which is equals to 543 mm. Having this xz and xy determined, next we need to determine the stress located at this plane. Why do we need to do that? By determining the stress here, we are able to determine the area stress here, which contribute to the shear force acting on this plane. Now, because of the moment acting in the major axis, the ultimate soil pressure will look something like this in the major axis. There will be P maximum and the P minimum due to the influence of the moment in the major axis. We have calculated the ultimate soil pressure previously when we defined the moment acting onto the peg footing. This formula was used, and the P max was obtained as 279 and P min was 136.9 kN per meter square. Use those values. We need to do interpolations to get your PS here. Assuming the stress is linearly distributed across the width of the peg footing. Through interpolations, you get your PS equals to 246.1 kN per meter. And then you find the area of the stress here. The stress here looks like a trapezoid. You can use the formulas to determine the area of the trapezoid in order to determine the shear force due to this stress area here. This is calculated by multiplying 1 per 2 with the summations of the PS and the P maximum, which is 279 plus 246.1, and then multiply the width, which is xz 556 mm. The area of the stress here will give you the plane shear force, which is in the units of kilonewton per meter width. You will need to convert this plane shear force into the total shear force acting at this region. You are talking about this plane multiply the width. Take this plane shear force multiply the width of the peg footing, which is 2.2 meter. That gives you a total of shear force equals to 321.2 kilonewton. You will do the same for the minor axis, since in this case there is no moment in the minor axis. You will assume that the stress it will be equally distributed. That gives you a rectangular stress here. Find the area of the stress here. That will give you the plane shear force. Take 208 kilonewton per meter square. Multiply this width, which is 543 mm. This gives you a plane shear force of 112.9 kilonewton per unit width. In the minor axis, we are referring to this shear plane, and the plane shear force it will be in these directions. In order for you to determine the total shear force, you're going to use the plane shear force multiply the width here, and this width shall be equals to the width in the major axis, which is 2.4 meter. That will give you the shear force of 271 kilonewton. Next, we're going to proceed with the calculations to determine the shear resistance of the peg footing, both in the major axis and the minor axis. First, we need to get the K which is in the functions of the effective depth. The effective depth in the major and the minor axis differ slightly. Substitute those values into the equations. You get k equals to 1.64. Make sure the calculated k is not exceeding 2.0. The calculated k here is less than 2.0. Then you may use the k calculated. Otherwise, you will use it as 2.0. Next, we need to determine the row 1, representing the relative areas of the reinforcement bar against the effective areas of the concrete. This AS here, it will be the reinforcement bar provided in the major axis and the minor axis. The effective depth is the one that we have calculated previously. Only that now the B here, you have to be careful. Let's say now we first deal with the shear resistance in the major axis. We are talking about this plane here, and the reinforcement bar that we are referring to, it will be arranging in this manner, crossing the shear plane here, which in this case it is the major reinforcement 1696, and then the B for these equations shall be taken as this width, not this width, since we are talking about this shear plane. And this B here is equals to 2.2 meter. This is how you get the row 1 equals to 0.00156. You will do the same to determine the row 1 in the minor axis. Now we are referring to this plane, and the AS, it will be based on this reinforcement, which is the reinforcement provided in the minor axis 1810 mm square. And then since that we are talking about this shear plane, we are talking about this width, which is 2.4 meter, and the effective depth in the minor axis, which is 482 mm. Substitute the value into the equations, you get 0.00156 also. Make sure the row 1 here needs to be less than 0.02. The calculated value is less than 0.02. Then you may use the calculated value. Otherwise, you will use 0.02. Now that you have your K and the row 1, you can now determine the VRDC and VRDC mean. Take the K calculated, substitute into the equations. Take the row 1 calculated into the equation as well. Use the FCK, which in this case, your FCK is equals to 30 Newton per mm square, and then the BD. For the major axis, your BD, it will be this plane. For the minor axis, your BD, it will be this plane. You will need to use the right B and right D for you to compute the numbers. You will do the same for VRDC mean. Substitute the K into the equation. FCK equals to 30, and then use the right BD to determine the VRDC minimum. Same process. The BD for the major axis is referring here, this B and the effective depth in the major axis. As for the minor axis, we are talking about this plane, and the B is now HC times the effective depth in the minor axis. Having the VRDC mean calculated, we can now determine the shear resistance, which is the greater value between the VRDC and the VRDC mean. You will do the same for the minor axis. Once you have concluded the shear resistance, compare the shear resistance with the shear force calculated earlier on based on the ultimate soil pressure. The resistance is 400 something, and the shear force at the shear plane of 1D from the column face was 300 something and 200 something. The shear resistance is greater than the shear load. Therefore, you can conclude that the shear plane at 1D from the column face is adequate to resist the shear load